folks a couple more minutes. While the last few folks maybe join in, just a little warning, today is going to be kind of similar to Tuesday, where we're going to do part of our activity, and then, so we're going to start discussion, part of the activity, and then finish the activity, then do more discussion, and then finish the activity. There's also sort of two parts of today's assignment. So first part should look normal. It has one of our quizzes, which is like the ungraded worksheet where I just give you a little bit of feedback. But I just want to see that you're thinking about it. And then also for today, I would like you, whenever you have a chance, to tell me a little bit about what you're thinking for your poster project. So some of you have already told me what you want to do. Awesome. You can just 2-word sentence and submit that. But if you haven't, if you've thought about it at all, if you haven't thought about it at all, that's also fine. But if you can tell me a little bit about maybe if there was something from this semester that stood out to you, or if you have a hobby or interest that I can relate to astronomy. I'm pretty good at relating random things to astronomy. That's kind of my job. Whatever whether or not you thought about it, just at the end, I will remind you that I do want just a short text where you are thinking about poster projects as part of today. With that, it looks like we have a fairly good group, so I will go ahead and get started. I guess before I do, any questions, concerns about the end of this batch or anything else? Oh, I will send out a study guide today. It's written, I just have to send it. And I will also send solutions to all of the in-class stuff with that. So that will be coming today, I promise. Test day will be next Thursday, but again, it won't be due for quite a bit after that. I think I have it set as the 29th, so you will have plenty of time. It will be in the study guide, I promise. And the material for this section is due the 24th, so that's the last day of classes. So even if you haven't done a homework assignment, if you haven't done any labs, there's still plenty of time, but now would be a good time again to start working on those. Like I said, any questions about any of that before we get going? Sweet. Okay, so today we are going to be talking about dark matter, which I am super excited for because dark matter is crazy fun to think about. That's what you guys voted for, so I'm happy. The last time I taught this class, I did the same choice thing and the students voted for dark energy, and that was much harder to talk about. Dark matter, there's a lot of cool things to talk about. The first thing to think about though is just to start by asking, what is dark matter? And the big answer to that is we have no idea. But the kind of more important answer is that we can break down this term dark matter into its 2 words. So matter is anything that has mass. So dark matter has mass, it bends space-time. Anything with mass bends space-time, interacts gravitationally. So dark matter is matter, it has mass, but it is dark, so it does not interact with light. And what that means is that not only does it not emit light, it also does not block, absorb, scatter light in any way or form. So, and this means that dark matter is not just like dust. This is how we distinguish dark matter from things like dust and planets that don't really emit much light, but they will block light. If there was a big chunk of dust between me and the screen here, you wouldn't be able to see me because there would be dust. But if there was a big thing of dark matter here, which there could very well be, you would still be able to see me because the light that is reflecting off of my face and hitting this camera would travel straight through it, no problem. So dark matter is dark, it does not interact with light, and it has mass and therefore is matter. We will talk about how we know dark matter is a thing, but one of the main ways we do is that when we measure the mass of a galaxy, we can see that the amount of mass in that galaxy does not match the amount of light in that galaxy. So galaxies have too much mass for the amount of stars, gas, and dust that they have. So we need some form of dark matter, so matter that does not interact with light and has mass, to balance this out, to fix this kind of mismatch between the amount of mass in a galaxy and the amount of light that galaxy is producing. And the last term I want to throw in here is that dark matter is non-baryonic. And so what that means is that everything we interact with is made up of baryons. Really specifically, so baryons are just normal matter. So really specifically, this is our standard model in particle physics. It should look sort of kind of like the periodic table. That's kind of what we were trying to go for. Physicists tried to find something where we could say, if we take all the particles in the universe and you plot them based on their properties, do you get something that looks sort of like a periodic table of elements? And it's like, not quite, but kind of. So these are all of the baryons in our universe, these 12 particles, these purple and green particles. Everything that you interact with is made up of these three particles here. So we have quarks. Up and down quarks make up protons and neutrons. So a proton is 2 up quarks and 1 down quark, and a neutron is 1 up quark and 2 down quarks. There are also more massive quarks, so as you go along this x-axis, you get more massive particles in this section here. So there's charm and strange quarks that are slightly more massive than up and down, and top and bottom quarks that are slightly more massive than the charm and strange quarks. All of the quarks in this column have the same charge, all of the quarks in this column have the same charge, and there seem to be pairs between charm and strange, top and bottom, and up and down. We also interact with electrons a lot because all of the elements, all of the atoms that we see are made up of protons, neutrons, and electrons, so the electron should look similar. And then muons and tauons, which are these kind of heavier versions of electrons, same charge, same -1 charge, just filling up the rest of our standard model. The last type of particle we have down here are neutrinos. So those are those things that we saw from the sun. We can measure the sun's neutrinos. They are produced whenever there is a fusion reaction. We do not think they are dark matter because we can detect neutrinos. They have mass. They do sort of interact with light in a way that dark matter doesn't. Also, in our particle standard model, we have some bosons. So these columns here, the gluon, the photon, and then the W and Z bosons are what control forces in the universe. So W and Z bosons allow for fusion to happen. It's what allow for particles to change type. Gluons hold protons and neutrons together inside of your atomic nucleus, and quarks together inside of your protons and neutrons. And then photons carry the electromagnetic force. So these are light particles. And then we also have our Higgs boson, which we are pretty sure exists and what gives things mass. So of these, Higgs probably interacts with dark matter, but none of the rest seem to. And we only have we're pretty sure we have detected the Higgs boson, but even that is a little fuzzy. So the main thing is this is everything we know of. Dark matter would be another particle on this once we figure out what dark matter is. Right now, we don't know what it is, and it is not part of our standard model of particle physics. But the big important thing is dark matter is matter, and it is dark. So from that, I'm going to kind of split up this lecture into 3-ish parts. First, I'm going to talk about how we measure dark matter. Then I'm going to talk about what we think dark matter might be. And then I'm going to talk about how we might detect those different dark matter particles. So I'm going to start by thinking about how we measure dark matter, and I think this is really important because I like to think of dark matter as almost an observation more than a theory. So we observe that galaxies have mass, and that mass does not match the amount of light they have, so they must also have dark matter. What that dark matter is, that's a theory, but that dark matter exists seems to me to be kind of an observation. And we have multiple ways that we have observed dark matter. So it's not just one measurement that we can't explain, it's hundreds and hundreds of measurements that we cannot explain without dark matter. So if anyone tells you that dark matter, they don't think it exists, tell them that they are probably wrong. Because we are pretty sure that dark matter does seem to be a thing, because every time we look at a galaxy, or at least almost every time we look at a galaxy, we see that they have too much mass for the amount of light that they see. Plus, we have other ways of measuring dark matter, and all of them just kind of corroborate this claim of dark matter existing. Any questions so far? Sorry, I've been kind of blasting through here. Okie doke. So our first way of measuring dark matter is by measuring the rotational speed of galaxies. So if you've done the Milky Way lab, this one gets into that a little bit. So that one, you look at the rotation curve of the Milky Way and compare it to our solar system. You also measure the rotational speed of the sun around the Milky Way, or use the rotation of the sun around the Milky Way to find the mass of the Milky Way. And we can do that because we're pretty sure that objects are rotating around disk galaxies are being held in orbit by gravity. That's the only force that's holding them in place. So we can use the law of gravity with the speed of how fast things are rotating to get an idea of the mass of a galaxy. And what we always see when we look at the rotation of disk galaxies is that, especially in their outer parts, they are rotating too fast for what we would expect if they were only made of visible matter. So that's what this graph is showing here. These points are different observations of a galaxy. And when you plot the velocity versus the distance from the center, we see that as you get further and further away, things actually start to speed up, which is the opposite of what you would expect if all the mass in the galaxy was in the disk, in this bulge and in the disk of the galaxy, which is what it looks like if you're only measuring stars. So this line here is what we would expect if there were only stars in this galaxy, and these points here are what we observe. This huge difference, especially at large radii, so big distances from the center of the galaxy, tells us there is some missing dark mass that we are not seeing, so there must be dark matter. On a little side note, I have to throw this in because this is one of my favorite astronomers. If you do want to do a biography project, this might be a good woman to look into. So Dr. Vera Rubin was one of the big persons who measured big leaders in the field measuring these rotation speeds of galaxies. So she measured rotations of hundreds of galaxies and found that every time she did it, there was too much mass. They were rotating too fast for the number of stars. So she pretty much confirmed that dark matter was a thing. But what's really amazing about Vera Rubin is that she was born in 1928. So she entered the field of astronomy when it was very much still a male-dominated field. Things have changed a lot in the past 20 or so years, and we're getting pretty close to gender parity in astronomy, which is awesome. But back when Vera Rubin was starting, like, astronomy was very much a male field. So she wasn't even allowed to meet with her advisor in his office because women weren't allowed in the part of campus that her advisor worked in. So just kind of went through a lot, but still did this incredible work that has shaped the field of astronomy in the past 100 or so years, or less than that. But the sad thing is she died in 2016 before the Nobel Prize Committee got their act together and gave her an award. And unfortunately, Nobel Prizes cannot be given to deceased people. So she will never get a Nobel Prize, despite the fact that she pretty much discovered dark matter, which is frustrating. But she will have a telescope named after her. So one of the next big ground-based telescopes will be called the Vera Rubin telescope. This is not the one that is controversial that might be being built on Hawaii. This is the Large Synoptic Sky Survey Telescope, will be named after her. So she is honored in astronomy, despite the fact that she never got a Nobel Prize, and she should have. Okay. But the big thing, her big discovery, was that every time she measured rotation rates of galaxies and just found again and again that the galaxies were rotating too fast for the amount of stars and gas in these galaxies. So with that, we are going to do the first part, of our dark matter activity. So in your assignments, this is, I think it should be day 20, but I rearranged things. So it's a day 21 dark matter, and there's this dark matter quiz. We're going to start with questions 1, 2, 3, and 4. 1, 2, and 3 use this little simulation that does not require flash, it should be fine, where we've got some data points, some observations of galaxy rotation, and you can make a blue curve model with different amounts of stars and dark matter, and you're going to try to, and also a supermassive black hole in the center. And you're going to try to find the best fit. So make this blue curve match the red points as best you can. And then use that to answer a couple questions. So I'm going to make some breakout rooms as I do. Are there any questions about any of this? I'm not hearing anything. So let's aim to join back together around noon-ish. So take about 12 or so minutes to answer questions 1 through 4.